Right now, under your feet, something is building. A crack in the earth 600 miles long has been silently charging for 12,000 years. Scientists just found out how close it is to snapping. We used to think the San Andreas was the big one to fear. We were looking in the wrong place. In this video, we follow the faults nobody watched, the hidden plates nobody counted, and the cities sitting on top of all of it. If you want to keep up with stories like this, subscribe. Let's go.
Pick up any map of American earthquake zones, and your eye goes straight to California, that long red line cutting through the state. 800 miles of cracked earth running from the Salton Sea all the way up past San Francisco. The San Andreas Fault. It has a name everyone knows, a history everyone fears, and billions of dollars worth of sensors watching every millimeter of its movement around the clock. That attention makes sense. The San Andreas has caused some of the most destructive earthquakes in American history. The 1906 San Francisco earthquake killed over 3,000 people and leveled most of the city. Scientists have been studying that fault for more than 100 years. They know its patterns. They know its danger zones. They have spent decades building systems to catch its next move before it happens. So why are geologists starting to sound genuinely scared? Because all that focus on one fault created a blind spot. A massive, dangerous, continent-wide blind spot. While every dollar, every sensor, and every research team pointed west at California, something else was happening. Slowly, quietly, underground. Fault systems stretching across thousands of miles of North American land were building up energy that nobody was measuring. Communities were growing on top of them. Pipelines and highways were built across them, and the science stayed frozen decades behind reality. A geologist named Susan Hough at the United States Geological Survey put it plainly: the places we do not watch are the places that will surprise us. She was right, and the surprises have already started arriving. Think about how a pressure cooker works. You seal it, you apply heat, and the steam has nowhere to go. The longer the lid stays on, the more violent the eventual release. Fault lines operate on the same idea, just on a timescale that makes human lifetimes feel like seconds. A fault can lock up for centuries, even thousands of years, absorbing stress from the slow grinding of tectonic plates. Every year of silence adds to the pressure. Every decade of calm makes the eventual rupture more powerful. The faults getting attention right now are the ones that stayed silent the longest. And that is the terrifying part. The San Andreas has ruptured many times in recorded history. Scientists have data on it. The hidden faults spreading across Alaska, the Pacific Northwest, and the American heartland have not ruptured in living memory. Some have not ruptured in thousands of years, which means the pressure gauge has been climbing this whole time with zero relief. Scientists recently looked at seismic data from regions that barely make the news. What they found shook the geological community. Fault systems previously labeled low risk or inactive are showing measurable strain. Some are past due for a major event. Some are so far past due that the slip deficit, meaning the stored movement waiting to release all at once, has reached levels that would make even a San Andreas expert uncomfortable. The biggest surprise was not in California at all, it was in Alaska, and it had been sitting there unnoticed for over a century, hiding in thick forest and frozen ground, stretching for hundreds of miles across one of the most remote and infrastructure-heavy corridors on the continent. Something was coiling beneath the wilderness, and in the next chapter, you will find out exactly what it is. Joseph Burr Tyrrell was used to finding things nobody expected. In 1884, he discovered the first large dinosaur skeleton ever found in Alberta, Canada, almost by accident while surveying coal deposits. The man had a gift for stumbling into history. In 1912, he was doing fieldwork in the Yukon when he noticed something strange cutting across the landscape. A long, straight trench, a deep scar in the earth running in an almost perfectly straight line. disappearing into the wilderness on both sides. The local terrain folded and shifted around it, like the land on either side had been sliding past each other for a very long time. Tyrrell recorded it, named it, wrote it up, scientists filed it, and then for the better part of a century, the world more or less forgot it existed. The fault bore his name for decades without attracting much serious study. The Tintina Fault, a geological curiosity from the early mapping era, a relic entry in scientific catalogues alongside hundreds of other labelled fractures that received no ongoing attention. It sat in the remote wilderness of interior Alaska and the Yukon, far from population centers, far from media cycles, far from funding committees in Washington. The problem with ignoring something is that ignoring it does not make it stop. While researchers looked elsewhere, the Tintina Fault kept doing exactly what fault lines do. It kept straining. The Pacific Plate and the North American Plate kept grinding against each other in complex ways that sent stress rippling hundreds of miles inland. The Tintina sits in what geologists call a transpressional zone, meaning the plates on either side are pushing into each other while also sliding sideways. Both motions at once, both building energy at once. Every year for over 100 years since Tyrrell recorded that trench, the fault absorbed more stress and released none of it. 0 ruptures of any significance, 0 major earthquakes to bleed off the pressure, just silent accumulation. By the time modern geologists started paying real attention, the numbers were already alarming. The detection tools that finally brought the Tintina back into focus did not exist in Tyrrell's time. Modern satellite radar systems can measure ground deformation down to fractions of an inch from orbit. Drone surveys can cover terrain in days that would have taken a ground team years to walk. Seismometer networks, when actually deployed, can detect the faint low-frequency tremors that hint at deep underground movement long before any surface shaking occurs. When researchers applied these tools to the Tintina in the early 2000s, they found a fault, very much alive. The strain rates were measurable, the locked sections were identifiable, the slip deficit, that stored-up movement waiting to discharge all at once, was calculable. And the number they calculated stopped people in their tracks. Tyrrell had mapped a scar. He had no way to know that scar was slowly winding itself tighter every single year. He could not have known that 113 years after he wrote it up in his field notes, scientists would be standing over the same trench with very different technology and very different expressions on their faces. The forgotten fault had an overdue bill, and the next chapter will show you exactly how large that bill has become. Stand on the International Space Station and look down at North America. Past the clouds, past the green and brown patchwork of forest and tundra, you can spot the Tintina Fault with the naked eye. That is how big it is. A straight trench cuts across the continent like a scar left by something enormous. It runs from the Yukon Territory in northeast Canada all the way down into the interior of Alaska, slicing through dense boreal forest, mountain ranges, and frozen ground for 621 miles. To put that in perspective, that is roughly the same distance as driving from New York City to Cleveland, Ohio. One continuous fracture in the earth. The trench it carves into the surface can be hundreds of feet wide in some sections. Rivers follow it, valleys formed along it. In some stretches, the land on either side of the fault has shifted so dramatically over millions of years that rock formations on the left side have no geological match with anything on the right. The two sides started in completely different places. The fault moved them apart. Geologists call this kind of feature a strike-slip fault, which means the main motion is horizontal. The land on one side slides past the land on the other, like two giant conveyor belts moving in opposite directions. The San Andreas is also a strike-slip fault. The difference is that the San Andreas sits right next to some of the most densely monitored land on Earth, and the Tintina spent most of the last century sitting under thick Alaskan forest with almost no one watching it. The sheer scale creates a specific kind of problem. A fault 600 miles long does not rupture all at once in a single earthquake. Different sections can lock and build stress independently. One locked section might sit calm for centuries while a section 50 miles away shows more activity. This means the risk is spread out across a massive corridor of land, and understanding that risk requires data from hundreds of miles of terrain, much of it deeply remote and difficult to access. Until recently, that terrain kept its secrets well. Satellites changed the equation. Researchers using radar imaging found that the Tintina's surface displacement, meaning the amount the ground on one side had moved relative to the ground on the other, pointed to decades of locked stress. The trench Tyrrell walked along in 1912 was the same visible feature, but the understanding of what was happening underneath it was completely new. And then came the drones. Teams of scientists flew surveying equipment over sections of the fault that human boots had rarely touched. They mapped fault lines hidden under forest canopy. They found secondary fractures branching off the main trench. They found sections of locked fault that had shown no movement in the entire historical record. One of the study teams described it as mapping a loaded weapon they had accidentally left unsupervised for 100 years. The size of the Tintina is striking enough on its own, but the numbers behind what is building inside it are something else entirely, something you need to understand before anything else in this story makes sense, and those numbers are coming in the next chapter. For most of its recorded history, the Tintina fault carried a label that made scientists feel comfortable ignoring it: geologically inactive, low hazard, a remnant of ancient tectonic activity with little relevance to modern risk assessments. Maps from the mid-20th century colored it gray, the color reserved for features that were interesting history, but not present danger. That label was wrong. The shift in understanding came gradually, then all at once. The gradual part was the slow improvement of detection technology over several decades. Satellite-based radar systems called interferometric synthetic aperture radar, or radar interferometry, became precise enough by the early 2000s to detect ground deformation at the scale of millimeters from hundreds of miles above Earth. Scientists began running these surveys over remote regions that had never received serious ground-level study. The Tintina showed up clearly. Ground on one side of the fault was moving relative to ground on the other side. The movement was tiny, barely measurable in any single year, but the pattern was consistent across multiple survey periods. The fault was not dormant, it was creeping, accumulating, building. Then came the drone campaigns. Teams from the Alaska Earthquake Center deployed unmanned aerial vehicles over sections of the fault buried under thick spruce forest and brushwood. The drones carried LiDAR sensors, which fire rapid pulses of laser light downward and measure the return time to build precise three-dimensional maps of the terrain below the vegetation. Strip away the trees digitally, and you see the raw earth underneath. Every ridge, every trench, every fracture. What the LiDAR revealed were sections of the Tintina that had experienced no visible surface displacement in the modern era, meaning no ruptures, no stress releases, nothing. The ground looked locked. The fault was holding everything in. The all-at-once moment came when researchers combined the satellite strain data with the LiDAR surface maps and cross-referenced the results with deep seismic reflection surveys, which used controlled sound waves to image the underground structure of the fault. The picture that emerged was a fault system under significant and measurable stress across multiple sections, simultaneously. Scientists at the Alaska Earthquake Center published their findings carefully, using precise academic language. But the implication underneath the careful language was stark. The Tintina was straining at a rate consistent with a fault building toward a major rupture. The strain was measurable, the locked sections were identifiable, and the stored energy was calculable. A team member described the moment of seeing the combined data for the first time. They had gone into the project expecting to confirm the old story: old fault, low activity, minimal risk. Instead, they were staring at a system that looked increasingly similar to the locked sections of the Cascadia subduction zone before it ruptures, one of the most feared earthquake scenarios on the west coast. The Tintina was alive. The next question was how alive? How much had it built up while the world was looking the other way? How much pressure was stored? And most urgently, what would happen when it finally let go? That answer comes down to one number, and the next chapter is all about that number, 0.2 of a millimeter. That is roughly the thickness of 2 sheets of paper stacked together. At its slowest, the Tintina fault moves that much per year. At its fastest, it strains at about 0.8 of a millimeter annually. Pick up a ruler and look at how short 1 millimeter actually is. Now imagine waiting an entire year to see movement that small. On the surface, that sounds like the least scary thing in geology. A fault that barely moves should be the safest kind. This is exactly the logic that kept the Tintina off the radar for so long, and it is also exactly backward. Fault lines do not move smoothly. They do not drift a little each day like a lazy river. They lock. The rough, jagged edges of rock on either side press against each other with enormous friction and grip, holding the 2 sides of the fault in place, while the deeper tectonic forces pushing them keep building. The strain accumulates in the locked rock, like tension in a stretched rubber band. The longer the lock holds, the more energy stores up, and the more violent the snap when the friction finally fails. A fault moving half an inch a year and rupturing every decade releases small amounts of stored energy frequently. The earthquakes are manageable. The cycle resets regularly. Think of it like a pressure valve that cracks open every few years to let off some steam. A fault moving less than 1 millimeter per year and not rupturing at all is a completely different machine. That fault is not releasing anything. Every fraction of a millimeter that it should have moved but did not becomes stored displacement, waiting. Scientists call this a slip deficit. The number grows every year, and the Tintina's slip deficit has been growing for a very long time, without any relief whatsoever. Here is the comparison that makes this real. The San Andreas Fault slips several centimeters per year in some sections, and triggers frequent smaller earthquakes that bleed off stress. The Tintina slips a fraction of that rate, in a region where the last major rupture occurred so long ago that no living person remembers it. The San Andreas has a busy pressure valve. The Tintina has a valve that has been welded shut. Every year of silence is one more year of loading. Every decade of calm is a decade of added tension in the rock. And the Tintina has had not years or decades but thousands of years of uninterrupted silence. Seismologists sometimes use the phrase seismic gap to describe a section of fault that has been locked and quiet for longer than its average rupture cycle. Seismic gaps are considered the highest priority targets for earthquake risk assessment because the longer the gap, the more energy is waiting to discharge. The Tintina is one enormous seismic gap, and when the number behind that gap finally came into focus, it stopped being a theoretical concern and became something far more urgent. The actual size of what is stored underground, expressed in feet rather than millimeters, is the kind of number that changes how you look at a map. That number is next. 12,000 years ago, the last ice age was ending. Glaciers were retreating across North America. Humans were just arriving in Alaska and the Yukon, following animal herds across the land bridge from Asia. Mammoths still walked the tundra, and the Tintina Fault locked up. Since that moment, the tectonic plates on either side of the fault have kept moving. The forces driving them have never stopped. The pressure has never paused. Every single year, for 12,000 years, stress has been feeding into that locked section of rock, with nowhere to go. Add it all up, and you get a slip deficit of nearly 20 feet. 20 feet is the length of a large moving truck. Imagine drawing a line across a road and placing a moving truck with its nose on that line. Now imagine that the ground on one side of that line needs to lurch forward the full length of that truck, all at once, in the span of a few violent seconds. That is what the Tintina is holding back right now. To understand why this is extraordinary, consider what slip deficit actually means in physical terms. The two sides of the fault should have moved 20 feet relative to each other over the past 12,000 years. The rock is locked, so they have not moved. But the force demanding that movement has never gone away. The plates are still pushing. The stress is still there. The ground is essentially storing 20 feet of motion in the form of compressed and twisted rock, waiting for the friction holding it together to finally give way. When it does, that 20 feet of stored displacement does not release gradually. It releases in seconds. The rock on one side of the fault lurches forward, the rock on the other side lurches the opposite direction, and the energy radiates outward through the ground in every direction as seismic waves. The bigger the stored displacement, the more violent the shaking. 20 feet of accumulated movement translates to an earthquake scientists estimate would exceed magnitude 7.5. For reference, the 1989 Loma Prieta earthquake that struck the San Francisco Bay Area killed 63 people, collapsed a freeway, and caused $10 billion in damage registered at magnitude 6.9. A magnitude 7.5 releases roughly 5 times more energy than that. And that estimate assumes only part of the fault ruptures. If a larger section goes simultaneously, the number climbs higher. The 20-foot slip deficit is a physical fact measured by satellite data and geological surveys. It exists in the rock right now. It is the geological equivalent of a coiled spring compressed as far as it can go, held in place by nothing more than the friction of rough rock surfaces pressing against each other. That friction has held for 12,000 years. It will not hold forever. Something has to give, and when it does, the communities living above that 20 feet of stored motion will feel every inch of it. Some of those communities have no idea the fault even exists. That is the next part of the story. Numbers on a seismic scale are easy to read and hard to feel. Magnitude 7.5. 7.5? It sounds almost moderate. Like weather on the warmer end of comfortable. Let a person who lived through one describe it instead. During the 1994 Northridge earthquake in Los Angeles, which reached magnitude 6.7, a woman sleeping in her apartment said the building did not shake, it snapped sideways. She described feeling her body lift off the bed, her furniture sliding across the room as if the floor tilted, and a sound like a freight train running through the walls. The shaking lasted about 20 seconds. When it stopped, her building had partially collapsed. 16 of her neighbors did not survive. Northridge was magnitude 6.7. A magnitude 7.5 earthquake releases roughly 8 times more energy than Northridge, 8 times the ground velocity, 8 times the duration of violent shaking. The buildings that survived Northridge were not built for 8 times that force. Here is what the physics actually produces. When a fault slips, it sends out 2 types of waves through the Earth. The first type, called primary waves, arrive fast and push the ground back and forth in the direction the wave is traveling. They cause a rolling, rumbling sensation. The second type, called secondary waves, arrive slightly behind and move the ground perpendicular to the wave direction, snapping it sideways. Secondary waves are the destructive ones. They tear at building foundations, snap steel beams, shear off the joints where walls meet floors. At magnitude 7.5 on the Tintina, the secondary wave energy radiating outward from the rupture point would produce ground acceleration powerful enough to throw objects off shelves at distances of over 100 miles from the fault. Closer to the fault, the shaking would be severe enough to liquefy certain types of soil, causing the ground to behave like thick liquid. Buildings sitting on liquefied soil do not shake, they sink and tilt. The shaking would last 60 to 90 seconds. That does not sound long. Count it out loud right now. 60 seconds of everything you can see moving violently in ways buildings were never designed to move. Aftershocks would follow, multiple aftershocks above magnitude 5.0 in the first 24 hours alone, each one capable of bringing down structures already weakened by the main event. The communities sitting in the Tintina's path were built with a different threat in mind, mostly flooding and permafrost damage, the normal hazards of Alaskan life. Earthquake loading requirements for buildings in the Tintina corridor were set based on the old assumption that the fault was quiet. That assumption is gone now. The 20 feet of stored motion is real, the energy it represents is calculable, and the towns sitting above it exist in a completely different reality today than they did before scientists ran those surveys. 2 of those towns have names, and the next chapter puts them on the map directly in the fault's path. Dawson City sits at a bend in the Yukon River, surrounded by hills that still carry the scars of the Klondike Gold Rush. Around 1,300 people live there year-round. The buildings are a mix of old wooden structures from the Gold Rush era and newer construction put up over the past few decades. Some of the old buildings already lean slightly, shifted by the freeze-thaw cycle of permafrost over the decades. They have never been tested by a major earthquake. Fairbanks is larger, around 30,000 people, with a university, a major military installation at Fort Wainwright, regional hospitals, and infrastructure serving much of interior Alaska. It sits roughly 90 miles from the Tintina fault zone, close enough that a major rupture would produce severe shaking at city limits. Neither city was built with a magnitude 7.5 earthquake in mind. Building codes in earthquake country are designed around the known hazard. California cities near the San Andreas have strict seismic requirements. Buildings must be anchored to their foundations in specific ways. Structural frames must flex rather than snap. Certain construction materials are restricted or reinforced. These rules exist because the San Andreas has ruptured within living memory and the threat is taken seriously. In Dawson City and Fairbanks, the Tintina was classified as a low-activity fault for most of the modern building era. Engineers designing hospitals, schools, water treatment plants, and apartment buildings in those cities used hazard models that did not account for a magnitude 7.5 rupture on a fault holding 20 feet of stored displacement. The seismic loading assumptions baked into those foundations and structural frames are simply wrong by the new data. Permafrost adds another layer of danger unique to this region. Large portions of both cities sit on permafrost, frozen ground that can behave relatively solidly in normal conditions, but loses its structural integrity under the right stress. Prolonged intense shaking can cause permafrost to thaw rapidly and the ground above it to collapse or shift. Buildings that appeared stable can settle dramatically or tip. A geotechnical survey conducted after the new Tintina findings were published found that several critical facilities in Fairbanks sit on soil types highly vulnerable to earthquake-induced settlement. These include ground near the river floodplain, where the soil composition changes significantly with depth. During a major earthquake, the shaking in those zones would amplify significantly compared to bedrock areas, a phenomenon called site amplification that can double or triple the effective force felt by a building. None of this is in the existing risk models for either city. The populations of Dawson City and Fairbanks are not the only ones in the fault's reach. Smaller communities dot the corridor between them. Villages, mining camps, remote facilities. Many of them have no seismic plans of any kind. It runs straight through the corridor that carries one of the most critical pieces of infrastructure in North America. That infrastructure is the subject of the next chapter, and its vulnerability changes the stakes of the entire story. 800 miles of steel pipe, 4 feet across, carrying crude oil from the oil fields of Prudhoe Bay on Alaska's North Slope all the way down to the terminal at Valdez on the southern coast. The Trans-Alaska Pipeline is one of the most significant pieces of energy infrastructure ever built on American soil. Roughly 14% of all United States domestic oil production flows through it. Engineers who built the pipeline in the 1970s knew they were building through earthquake country. Alaska is one of the most seismically active places on the planet, The 1964 Good Friday earthquake that struck south-central Alaska reached magnitude 9.2, the most powerful earthquake ever recorded in North American history. The pipeline's designers were serious about seismic risk. They engineered the pipeline to handle the specific threats they knew about. The pipeline crosses the Denali Fault, and when that fault ruptured in a magnitude 7.9 earthquake in 2002, the pipeline survived. Engineers had designed the supports in that section to allow the pipe to slide sideways on sleds, absorbing the lateral ground displacement without rupturing. The pipe slid about 18 feet during the Denali quake. The sleds did their job. Not a drop of oil spilled. That engineering solution was built for the Denali Fault. The sections of the pipeline crossing the Tintina Zone received no equivalent treatment. The Tintina was classified as a low-hazard feature when the pipeline was designed and built. Engineers applied standard construction methods to those sections. The supports are fixed. The pipe has limited ability to accommodate sudden lateral displacement. A 20-foot ground shift, the stored deficit now sitting in the locked sections of the Tintina, would subject those sections of pipe to forces they were never designed to survive. A pipeline breach in a remote Alaskan wilderness location during the chaos of a major earthquake presents a cascading set of problems. Emergency response in interior Alaska is measured in hours and days, not minutes. Containment of a large spill in frozen terrain is extraordinarily difficult. The environmental damage to river systems and wildlife habitat would be immediate and long-lasting. And the economic disruption of taking a pipeline carrying that volume of oil offline, even temporarily, would radiate across the entire national energy supply chain. The pipeline's operating company has acknowledged the new Tintina findings and indicated that assessment of the relevant crossing sections is ongoing. No retrofit timeline has been announced. No engineering solution has been publicly confirmed. Oil kept moving through the pipe while the assessment began. The pipe crossed the fault zone. The fault zone held its stored displacement, and the clock that nobody can read kept ticking. Beyond the pipeline, the Tintina corridor carries major highways, power transmission lines, and communication infrastructure linking communities across the interior. All of it sits above the same locked fault. All of it was built on the same outdated assumptions. The next chapter takes you further away from the fault itself to a place that should feel safe by distance alone. But the physics of shockwaves does not care about distance in the way most people expect. Most people think of earthquakes the way they think of a loud noise at a concert. The closer you are to the speaker, the louder it gets. Stand far enough away and you hear nothing. A fault ruptures in Alaska. It shakes Alaska. Montana, several hundred miles to the south, stays quiet. That intuition is wrong in ways that matter enormously. Seismic waves travel through the earth, through rock and sediment and soil, and they do not fade out evenly. They travel fastest through hard, dense rock, and slow down when they hit softer sediment. When they slow down, something counterintuitive happens. They compress. All the energy that was spread out across a fast-moving wave in hard rock gets squeezed into a slower-moving wave in soft sediment. The wave gets taller. The shaking at the surface gets stronger. This effect is called seismic amplification, and it can boost the intensity of ground shaking dramatically in certain locations far from a fault's epicenter. The geology between Alaska and Montana is not uniform hard rock. The region contains river valleys, ancient lake beds, and deep basins filled with soft sediment deposited over millions of years. These sediment-filled basins act like bowls of jelly. When a seismic wave enters a jelly bowl, it sloshes back and forth, bouncing off the basin walls and amplifying as it goes. Cities built in river valleys, on old lake beds, or on delta deposits can experience shaking several times more intense than a city sitting on solid bedrock the same distance from the fault. Seismologists studying the Tintina's potential rupture ran wave propagation models, meaning they simulated how energy from a magnitude 7.5 event would travel south through the varying geology of the region. The results showed that communities in parts of northern Montana, sitting hundreds of miles from the fault, could experience shaking strong enough to crack masonry, fracture older building foundations, and damage unreinforced structures. The 1911 New Madrid earthquakes provided a historical case study for this exact phenomenon. That fault system sits in the central United States, thousands of miles from the East Coast. The shaking was felt as far away as Washington and Boston. Church bells rang in Massachusetts. The energy traveled through the soft sediment of the Mississippi embayment and amplified along the way. A magnitude 7.5 on the Tintina would send energy south through a geological corridor that includes portions of soft river sediment, exactly the kind of terrain that amplifies rather than absorbs seismic waves. Montana communities have no earthquake early warning infrastructure. Building codes in most of the region were set for minimal seismic risk. Hospitals, schools, and bridges in towns built on river valley sediment have no seismic reinforcement plan specific to a Tintina-type event. They did not need one under the old model. The old model is gone, and the shaking that could arrive in Montana would come with the worst possible addition for any community in its path: 0 seconds of warning. Why that warning system does not exist, and what happens in its absence, is the chapter that follows. On the morning of October 17, 1989, millions of people across the San Francisco Bay Area were going about their day when the Loma Prieta earthquake struck at 5:04 in the afternoon. There was no warning, no alarm, no 30-second countdown to take cover. The shaking arrived, and it stopped, and 63 people were dead. That was in one of the most monitored seismic regions on Earth. Today, California and the Pacific Northwest have something better. The Shake Alert early warning system operated by the United States Geological Survey detects the first fast-moving primary waves from an earthquake the moment they reach a sensor. Since primary waves travel faster than the more destructive secondary waves, the system can send alerts to phones and automated systems in the seconds between the first wave's arrival and the destructive wave's arrival. In some locations, that gap is 30 seconds. In others, it is 10. Even 5 seconds is enough time for a person to drop, cover, and hold on. Enough time for an automated system to halt a train, open fire station doors, or pause a surgical robot mid-procedure. The Shake Alert system in California has already proven itself in multiple events. The Tintina Fault has no equivalent system. The Alaska Earthquake Center operates a seismic monitoring network, but the density of sensors along the Tintina corridor is a fraction of what California has. Remote terrain, extreme weather, and a lack of dedicated funding have left vast stretches of the fault effectively unwatched in real time. The sensors that exist were placed and funded based on the old hazard classification: low risk, low priority, low coverage. A rupture originating on the Tintina in a remote section of interior Alaska would generate its first detectable signal at whatever sensors happen to be nearby. The warning chain from that detection to an alert reaching a phone in Fairbanks or a control room managing the Trans-Alaska Pipeline would take longer than the secondary waves take to travel the distance. In practical terms, this means 0 warning. The shaking arrives. Then the alert arrives, if it arrives at all, after the shaking has already started. The system designed for a slow-building hazard gives no protection against a sudden rupture on a fault nobody was adequately watching. Scientists at the Alaska Earthquake Center have formally requested expanded sensor deployment along the Tintina corridor. The request has been pending in various funding review cycles. No deployment timeline has been confirmed. The monitoring gap remains. Every day that passes without expanded sensor coverage is another day where a rupture on one of North America's most stressed fault systems could strike with no notice to the communities in its path. No automated systems would slow the trains. No alerts would reach the pipeline operators. The shaking would simply arrive. This is the reality sitting underneath Dawson City, Fairbanks, and the corridor between them right now. But the Tintina is only one piece of a much larger and stranger picture. While scientists were unraveling the story in Alaska, something even more unsettling was happening thousands of miles to the south. And the next chapter takes you there. Drive north out of San Francisco on Highway 1, past the vineyards and dairy farms of Marin County, up through Sonoma and into Mendocino County. The coastline gets wilder, the cliffs get higher, the ocean hits harder. By the time you reach the town of Eureka in Humboldt County, you are about as far from the polished earthquake research centers of the Bay Area as you can get while still being in California. 40 miles offshore from that coast, under roughly a mile of cold Pacific seawater, lies one of the most geologically complicated places in the Western Hemisphere. Scientists call it the Mendocino Triple Junction. The name comes from the idea that three major tectonic plates come together at this single point: the Pacific Plate moving northwest, the North American Plate sitting relatively still, and the Juan de Fuca Plate diving east beneath North America in a process called subduction. At the Triple Junction, these three plates all interact simultaneously, creating a zone of intense seismic and volcanic activity. A triple junction is already unusual. The physics of three plates meeting at one point produces a tangle of fault lines, subduction boundaries, and stress transfer zones that is difficult to model and even harder to monitor from land. The Mendocino Triple Junction has generated significant earthquakes throughout recorded history, including events above magnitude 7.0. Seismologists classified it as high risk, put monitoring equipment in place, and worked with the assumption that the three-plate model was adequate. For decades, that assumption held. The math was complicated but manageable. The monitoring made sense for what the model said was happening. Then a team of researchers decided to look deeper. They deployed a temporary network of ocean bottom seismometers, specialized sensors designed to sit on the seafloor and detect ground motion directly from beneath the water. The data they collected was supposed to validate the existing model, give the three-plate picture better resolution, fill in some of the detail. What the data showed instead was a subsurface structure that matched no existing model at all. The signals coming from beneath the Mendocino Triple Junction described a geometry that three plates alone could not produce. There were movement signatures coming from directions that made no sense under the accepted framework. There were stress signals from depths suggesting a more complex layering of rock than anyone had mapped. The team sat with the data for months before publishing. They checked their instruments, they cross-referenced with historical seismic records, they ran the numbers multiple times. The conclusion held every time. The Mendocino Triple Junction was hiding something. The three-plate model was incomplete. And the implications of what was actually down there, once the team finally put it into words, were going to force a significant reassessment of the earthquake risk for an enormous stretch of Northern California coastline. What comes next is something that makes the three-plate picture look almost simple. The paper landed in the geological community the way a fire alarm lands in a quiet library. A team of researchers working with a network of seismometers planted on the ocean floor off Northern California published findings that rewrote the fundamental structure of the Mendocino Triple Junction. The accepted picture, three plates meeting at one point, was incomplete. The real structure contained 5 moving tectonic pieces, not 3. 2 of those pieces were entirely hidden. They existed below the surface with no visible expression at the ocean floor or the California coastline. No geologist had walked over them. No surface survey had caught them. They were detectable only by the deep earth sound waves that the ocean bottom sensors had been patiently recording. Here is the way to picture a tectonic plate. Imagine the Earth's outer layer as a cracked eggshell. Each large piece of shell is a plate, moving slowly in a direction driven by the churning of hot rock deep below. Where 2 pieces meet, something dramatic happens. They can slide past each other, they can collide and crumple, or one can dive beneath the other. At the Mendocino Triple Junction, all of those interactions are happening at once. And they were happening with 2 extra pieces of shell that the scientific community did not know existed. The first hidden piece sits at the southern end of the Cascadia subduction zone, which is the massive fault system responsible for the most feared earthquake scenario on the west coast. At that location, a chunk of the North American plate has fractured off and begun to sink downward, dragged by the subducting Juan de Fuca plate beside it. This broken fragment was invisible in surface surveys because it sits entirely below the sea floor, descending into the mantle. The second hidden piece is called the Pioneer Fragment. It lies south of the Cascadia boundary, where the Pacific Plate meets the North American Plate. The Pacific Plate has been pulling a mass of ancient rock beneath the surface of North America. That rock mass, the Pioneer Fragment, travels along a hidden horizontal fault that lies completely below the seafloor. Its presence was completely absent from every risk model previously applied to Northern California. 2 hidden moving pieces, 2 sets of interactions that existing earthquake models were not accounting for. The scientific community's response was a controlled version of alarm. Research groups began revising their models. Funding applications for more sensor deployments went out. Scientists who had spent careers studying the Mendocino zone had to sit with the uncomfortable reality that the system they thought they understood was operating with hidden variables. What those hidden variables mean for earthquake risk in Northern California is a number that previous models had no mechanism to produce. And that number is larger than the estimates that have been guiding emergency planning for years. How much larger and what the Pioneer Fragment actually is comes next. The way scientists see underground without digging is by listening. Sound travels through rock the way light travels through glass, bending and reflecting when it hits boundaries between different materials. When an earthquake happens, it sends out sound waves in every direction, and those waves bounce around inside the earth before reaching the surface. By recording those waves at multiple points on the surface and working backward through the math, scientists can reconstruct a picture of what the underground structure looks like. The technique is called seismic tomography, and it produces images of the Earth's interior the way a medical scanner produces images of the inside of a human body. The detail in those images depends on 2 things: the quality of the sensors and the quantity of events to analyze. Dense sensor networks covering a large area produce sharper images. More earthquakes, even small ones, provide more data to work with. The ocean bottom seismometer network deployed off Northern California gave researchers both things at once. Sensors on the seafloor captured ground motion directly from beneath the water, far closer to the underground structures of interest than any land-based sensor could get. And the Mendocino zone generates enough low-level seismic activity that the researchers had thousands of small events to analyze over the deployment period. The image that emerged from that analysis showed 2 distinct rock masses moving in ways that were completely separate from the 3 known plates. The movements had direction, velocity, and depth signatures unique enough that no interpretation other than independent moving bodies fit the data. One mass was descending. The broken fragment from the North American plate at the southern end of the Cascadia zone was sinking at an angle, dragged downward by the plate subducting beside it. Its depth placed it entirely below the reach of any surface observation. Nothing on the seafloor above it revealed its presence. No ridge, no trench, no visible feature gave it away. The other mass, the Pioneer Fragment, was moving horizontally along a fault plane that sat completely beneath the sea floor. It was sliding laterally, carried by the motion of the Pacific Plate grinding against the North American Plate. The fault surface along which it moved had never appeared in any geological map of the region. Researchers described the experience of seeing these bodies in the tomographic images as disorienting. The established picture of the Mendocino zone had been built over decades by hundreds of scientists using every surface and near-surface method available. And 2 significant moving bodies had been sitting right there the whole time, invisible, doing their own thing underneath all of it. The hidden geometry matters because fault systems interact, stress, does not stay in one place. When one mass moves, it changes the pressure on everything around it. The hidden fragment descending near Cascadia was changing the stress distribution on the southern end of the Cascadia fault system. The Pioneer fragment's horizontal motion was loading stress onto the base of the San Andreas. Two moving bodies nobody knew about were already influencing two of the most watched fault systems in North America. And what the Pioneer fragment actually is, where it came from, and what it was before it disappeared underground, is one of the strangest stories in all of North American geology. About 30 million years ago, the Pacific Ocean floor looked completely different than it does today. A massive tectonic plate called the Farallon Plate covered most of the eastern Pacific. It stretched thousands of miles, and it was slowly diving beneath the western edge of North America in a continuous subduction process. As it dove, it pushed mountain ranges up, fed volcanic chains, and shaped the entire western face of the continent. California's Sierra Nevada mountain range, the Cascade volcanoes, and much of the Pacific Northwest coastline exist because of the Farallon Plate. Then the Farallon Plate largely disappeared. Subduction consumed it. As the plate dove into the mantle beneath North America, the portion of the plate still at the ocean surface kept getting smaller. The Farallon Plate was being eaten from below faster than new seafloor material could replace it. Over millions of years, it fragmented and shrunk. The Juan de Fuca Plate off Oregon and Washington is one of the Farallon Plate's surviving remnants. So is the Cocos Plate off the coast of Mexico. And so, it turns out, is the Pioneer fragment. The Pioneer fragment is a piece of the Farallon Plate that got left behind. Instead of continuing to subduct fully into the deep mantle, it broke off and became trapped in the horizontal shear zone between the Pacific Plate and the North American Plate. There it sits, a ghost of a vanished ocean, carried along by the Pacific Plate's motion while sliding along a hidden fault surface deep below the seafloor. It is ancient rock that formed on the ocean floor tens of millions of years ago, when the continents were in different positions and the Pacific Ocean covered a greater portion of the globe. Rock that has traveled hundreds of miles from where it originally formed, carried by tectonic conveyor belts too slow for any human timescale to perceive, but persistent enough to reshape entire continents. The Pioneer fragment's journey is not over. It is still moving. The Pacific Plate is still carrying it northward and pressing it against the base of North America. Every year, the stress on the boundary between the Pioneer fragment and the overlying plate increases slightly. That stress feeds into the fault network above it, adding pressure to systems that extend all the way up to the surface. The part of that surface network receiving the added stress includes the southern end of the San Andreas Fault and the base of the Cascadia subduction zone. Two systems already under significant independent stress. Two systems already overdue for major events in the assessment of most seismologists working on West Coast hazards. And now there is a hidden passenger under the floor, pressing from below, that the risk models had never included. The Pioneer fragment's discovery forced scientists to ask a new question. If the existing stress models for the Mendocino zone, built without knowledge of two hidden moving bodies, had already estimated a possible magnitude 8 earthquake at that junction, what did the updated model produce? The answer to that question changed the number, and the direction it changed was not down. Earthquake risk models are built on a foundation of known variables. Where are the fault lines? How fast do they move? How long have they been locked? What is the maximum magnitude a given fault section can produce? Those inputs go into a calculation, and the output is a probability. A 1 in 10 chance of a magnitude 7+ earthquake in the given region within the next 50 years. A 30% chance of a major event on the Hayward Fault by 2043, numbers that planners, engineers, and emergency managers use to decide how much reinforcement a building needs, where to stockpile emergency supplies, and how to allocate preparedness funding. Every single one of those models for Northern California was built without the Pioneer fragment and without the hidden descending slab at the Cascadia boundary. Two missing inputs of a complex system do not produce small errors, they produce compounding errors. Each wrong input feeds into the next calculation, shifting the output further from reality. When researchers began running the updated model, including the pioneer fragment's motion and the hidden fragment's descent, the changes rippled through the entire probability landscape for the region. The stress transfer calculations changed first. Stress released by one fault section can either increase or decrease the stress on nearby sections, depending on the geometry. The pioneer fragment's horizontal motion was adding stress to the base of the San Andreas system in ways the old model attributed to the Pacific Plate alone. The numbers were similar but not identical, and in earthquake modeling, small differences in stress distribution can shift the estimated maximum magnitude of an event by a measurable amount. The depth geometry changed second. The hidden descending slab near Cascadia altered the calculated behavior of the southern end of the Cascadia Fault. Cascadia is already the source of North America's most feared earthquake scenario, a potential magnitude 9 event that would strike the Pacific Northwest with devastating force. The southern end of Cascadia, closest to the Mendocino Zone, is where the fault system transitions from the main subduction interface to the complex tangle of the triple junction. That transition zone is where the geometry matters most, and the hidden slab was changing the geometry. The maximum magnitude estimate for a Mendocino Zone event moved upward in the revised model. Scientists are careful about stating exact new numbers publicly before peer review and replication are complete. The published language is cautious, but the direction is clear. The estimate for what the Mendocino Zone can produce is higher after the discovery than it was before, higher than the number that guided the building codes in Eureka, Humboldt County's largest city, sitting about 40 miles from the junction, higher than the number used to design the harbor infrastructure at Crescent City, a coastal community that was devastated by tsunami waves generated by a distant Chilean earthquake in 1964. Higher than the number embedded in the emergency response plans of Northern California counties that have been planning for a serious event, but perhaps not for the most serious event, the updated geology now suggests is possible. Two hidden plates, one very large number that needs to move upward, and a fault system sitting north of all of it that is already living on borrowed time. That system is next. Before the ocean bottom sensors went in, the standard working estimate for the maximum earthquake the Mendocino Triple Junction could generate was magnitude 8. For most of the public, magnitude 8 is an abstract number. Here is something more concrete. The 2011 Tohoku earthquake in Japan, the one that triggered the tsunami and the Fukushima nuclear disaster, registered magnitude 9. Magnitude 8 is one full unit lower on the scale, but the Richter scale is logarithmic, meaning each whole number represents roughly 32 times more energy. Magnitude 9 releases about 32 times more energy than magnitude 8. Both are catastrophic. Magnitude 8 is simply catastrophic for a shorter duration and over a smaller area. The Mendocino Zone at magnitude 8 would produce shaking across Northern California powerful enough to collapse unreinforced masonry buildings throughout Humboldt and Mendocino counties. Landslides would block coastal highways for weeks. The regional infrastructure serving roughly 300,000 people would be severely disrupted. That estimate assumed 3 plates. The updated model has 5. When researchers ran the revised stress calculations with the pioneer fragment and the hidden descending slab factored in, the maximum credible earthquake estimate at the Mendocino Zone did not stay at magnitude 8. The additional stress loading from the 2 hidden bodies adds to the total energy budget available for a rupture. The fault surfaces involved in the most extreme scenario are larger than previously mapped because the hidden bodies extend the active fault geometry below what the old model captured. Scientists publishing on this topic use phrases like potentially underestimated and warrants further assessment. In scientific communication, those phrases carry real weight. They mean the old number was a lower bound and the actual maximum could be higher. A magnitude 8.5 releases about 5.5 times more energy than a magnitude 8. The difference on the ground is not a slight increase in shaking, it is the difference between severe damage and total destruction across the same region. It is the difference between a hospital that loses power and a hospital that loses its roof. The tsunami risk compounds the ground shaking risk. A larger rupture at the Mendocino zone would displace more ocean water than a smaller one. Humboldt Bay, the largest bay on the California coast north of San Francisco, sits directly in the potential tsunami inundation zone. Eureka, a city of around 27,000 people, wraps around that bay. Much of the developed waterfront sits on low-lying ground a few feet above sea level. Crescent City, 80 miles north of Eureka, has already demonstrated its tsunami vulnerability. It sustained serious damage from the tsunami generated by the distant 1964 Alaska earthquake, which occurred at magnitude 9.2 but originated thousands of miles away. A large earthquake originating 40 miles offshore would produce a local tsunami arriving in minutes, far faster than any evacuation could be completed. This is the updated picture of the Mendocino Zone, a place already ranked among the most seismically active in the United States, now carrying revised estimates that push the risk ceiling higher. Built on a junction that turns out to be far more complex and far more dangerous than the model everyone was using. And the Mendocino Zone does not sit in isolation. It sits at the southern boundary of the largest and most feared subduction zone in North America. That is the next chapter. Drive north from the Mendocino Triple Junction along the California coast, and within a few hours you cross into Oregon. The scenery shifts, the coastline gets bigger, the waves hit harder. Somewhere offshore, invisible beneath hundreds of feet of ocean water, one of the most dangerous geological structures on Earth begins. The Cascadia subduction zone stretches roughly 700 miles from northern California all the way up to Vancouver Island in British Columbia, Canada. Along its entire length, the Juan de Fuca Plate is sliding beneath the North American plate at a rate of about 1.5 inches per year. The junction between the two plates is locked across most of that distance, storing energy the same way the Tintina stores energy, but on a scale that dwarfs anything in Alaska. Scientists estimate the locked section of Cascadia has enough stored energy to produce a magnitude 9 earthquake. The last time it fully ruptured was January 26, 1700. The shaking was so powerful that indigenous oral histories recorded the ground rolling like waves on the ocean. The tsunami it generated crossed the entire Pacific and caused documented damage in Japan. Geologists found a layer of sand buried under coastal marshes from California to Canada, deposited in minutes by the wave that swept inland when the seafloor lurched upward. That was 325 years ago. The average time between full Cascadia ruptures, based on geological evidence from buried sediment layers, is roughly 200 to 500 years. The last one was at the long end of that range. Seismologists describe Cascadia as fully locked and capable of rupturing at any point. Some researchers put the probability of a major Cascadia event within the next 50 years at roughly 1 in 3. The Mendocino Triple Junction sits at Cascadia's southern end. Before the new plate discoveries, the southern end of Cascadia was considered the weakest and least likely section to drive a full rupture. The geometry there was complicated by the transition to the Triple Junction, and models suggested a full rupture would probably start further north and propagate south. The southern end was almost an afterthought in the full rupture scenarios. The hidden descending slab near the Cascadia boundary changes that picture. That slab is pulling on the southern end of the locked Cascadia interface from below, adding a downward stress component that previous models did not include. The Pioneer fragment pressing horizontally from the south adds lateral stress to the same region. The southern end of Cascadia is receiving stress from two hidden sources that the standard model never accounted for. Whether that additional stress makes the southern end more likely to initiate a rupture or simply changes how a rupture propagates once it begins is a question geologists are actively working through. The calculations are complex. The data is still being processed, but the direction of the finding is consistent. The southern end of Cascadia is under more stress than the previous model showed. A Cascadia rupture starting at the southern end, near the Mendocino zone, could behave differently than a rupture starting further north. The fault geometry at the southern end is irregular, shaped by the complex intersection with the triple junction. An irregular rupture front can produce more violent ground motion in certain directions. It can also generate a more complex tsunami wave pattern, with energy focused differently across the coastline. Two systems, each capable of catastrophe on their own, now appear connected by hidden stress pathways that science is only beginning to map. The math connecting them is still unfinished, and that unfinished math is exactly what makes the next chapter so important. In most fields of science, when you discover that a system is more complex than you thought, you update the model and move forward with better predictions. The updated model gives you better answers than the old one. Progress runs in one direction. Earthquake science at the Mendocino zone is currently in a different situation. Researchers have identified two hidden moving bodies that the previous model missed entirely. They have begun incorporating those bodies into new stress calculations, and the more complete picture is, in some ways, more uncertain than the simpler one it replaced. Here is why. A two-body interaction between two tectonic plates is complicated enough. Add a third and the interactions multiply. The stress change on any one boundary depends on what every other boundary is doing simultaneously. 5 moving bodies in close proximity, each influencing the others, produce a system where small changes in the behavior of one piece cascade through the entire network in ways that are genuinely difficult to predict, even with sophisticated computer models. Geophysicists call this problem stress interaction, and it sits at the frontier of current earthquake science. The basic physics is understood. Stress redistribution follows known laws. The problem is that the inputs, the exact geometry, the friction properties of each fault surface, the rate of motion of each body, need to be known with a precision that current measurement technology cannot fully provide. Researchers working on the Mendocino system know the broad outlines. The Pioneer fragment moves roughly north to northwest, carried by the Pacific Plate. The hidden descending slab moves downward and eastward, pulled by subduction. The Juan de Fuca Plate dives northeast. The North American Plate sits. The Pacific Plate moves northwest. 5 motions in 5 different directions, all interacting at a single junction, all capable of changing stress on any of the others. What the current models cannot predict is the chain reaction scenario. If the Pioneer fragment's motion suddenly increases stress on the San Andreas above a critical threshold, does the San Andreas rupture? If it does that stress transfer northward along the coast toward the Cascadia boundary? If it reaches Cascadia's already loaded southern end, does it push a locked section past its breaking point? Each of those questions carries a genuine unknown. Researchers can model scenarios, they can estimate probabilities, but the specific sequence and timing of events in a multi-fault chain reaction at this junction cannot be predicted with the precision that would make an early warning useful. A team working on the Mendocino seismic network described it as trying to predict the exact moment a pile of sand collapses when you keep adding grains. The physics of each grain is simple. The behavior of the pile is not. This is an honest scientific frontier. Researchers are not hiding uncertainty or downplaying risk. They are working at the edge of what the tools can currently resolve. More sensors, longer data records, and faster computing will sharpen the picture over time, but sharper pictures take years to build. The communities on the Northern California coast, the cities at the edge of the Cascadia zone, and the infrastructure serving millions of people along the Pacific seaboard are living inside that uncertainty right now. The science is catching up, but not fast enough. And the strangest part of this entire story is that the most dangerous hidden fault in terms of pure population exposure sits nowhere near Alaska or Northern California. It sits in the middle of the country, under cities that rarely run a single earthquake drill. Stand at the corner of Main Street in Memphis, Tennessee, on any given morning. Watch the traffic move. Watch people head into coffee shops and offices. Watch delivery trucks roll past brick storefronts. Nothing in the scene suggests any connection to seismic danger. Memphis sits in the American South, hundreds of miles from the Pacific coast, hundreds of miles from any mountain range. Earthquakes happen in California. Everyone knows that. Underneath Memphis, a fault system is winding tighter. The New Madrid seismic zone stretches roughly 150 miles through the central United States, passing through parts of Missouri, Arkansas, Tennessee, and Kentucky. The city of Memphis sits near its southern end. St. Louis sits near its northern end. The zone runs along the ancient buried Rift Valley, where the North American continent nearly split apart roughly 500 million years ago. That ancient rift is a permanent weakness in the crust, a healed scar that never fully closed, and it remains capable of producing violent earthquakes today. The New Madrid Zone is the most seismically active fault system east of the Rocky Mountains. Most residents of Memphis and St. Louis have no idea. This is partly a story about memory. The most powerful earthquakes to ever strike the continental United States east of the Rockies occurred on the New Madrid Fault between December 1811 and February 1812. 3 separate earthquake sequences, each reaching or exceeding magnitude 7, struck within weeks of each other. The shaking was felt across an area stretching from Canada to the Gulf of Mexico. Church bells rang in Washington. Cracks opened in the ground across Tennessee. Entire sections of forest collapsed into the earth, and the Mississippi River ran backwards. That last detail sounds like exaggeration. It is not. The ground deformation during the 1812 sequences temporarily reversed the flow of the Mississippi in certain stretches, creating new lakes, rerouting channels, and swallowing entire islands. Eyewitnesses described the river boiling, churned from below by escaping gas and displaced sediment. The 1812 earthquakes occurred when the surrounding region was sparsely populated. The cities of Memphis and St. Louis were small frontier settlements at the time. Total deaths were in the dozens, a tragedy, but manageable given how few structures existed to collapse. The region is no longer sparsely populated. Memphis has around 600,000 people in its city limits, and over 1 million in the surrounding metro area. St. Louis has similar numbers. The corridor between them contains some of the most important infrastructure in North America: the Mississippi River shipping network, major rail lines, interstate highways, and a web of energy pipelines crossing beneath the river basin. A large New Madrid event today would arrive in a region that has largely planned for floods, tornadoes, and heat, not earthquakes. Buildings across the zone were constructed without meaningful seismic standards. Bridges across the Mississippi were not uniformly designed for major ground shaking, and most residents have never practiced an earthquake response of any kind. The fault that almost no one in Memphis talks about is the one sitting directly underneath them, and its history is far more extreme than the polite geological terminology suggests. December 16th, 1811, 2:30 in the morning. The town of New Madrid, Missouri, population around 1,000 people, jolted awake to a sound survivors described as 1,000 cannons firing at once. The ground heaved. The Mississippi River churned. Trees snapped. The ground cracked open in dozens of places, venting sand and water upward in geysers called sand blows, some reaching heights of several feet. The first shock reached an estimated magnitude 7.7. The shaking lasted several minutes. This was only the beginning. Over the next 2 months, the region experienced hundreds of aftershocks, dozens of them strong enough to feel hundreds of miles away. Then, on January 23rd, 1812, a second major earthquake struck, reaching an estimated magnitude 7.5. Communities along the Ohio River reported boats thrown onto shore. Chimneys collapsed across Kentucky and Tennessee. The shaking reached Canada. On February the 7th, 1812, the largest event of the sequence hit. Seismologists studying the geological evidence now estimate it reached magnitude 7.7 to 8. The land surface in the rupture zone heaved several feet upward and then dropped. The Mississippi River, one of the most powerful rivers on Earth, moving millions of gallons of water southward every second, reversed direction in sections near the fault zone. The reversal lasted hours. It happened because the earthquake pushed sections of the riverbed upward, creating a temporary dam. Water piled up behind the new elevation and surged backward upstream. When the ground dropped again, the stored water released as a massive wave downstream. New islands appeared. Old islands vanished. A large new lake, now called Reelfoot Lake in Tennessee, formed where flat farmland had existed the day before. It still exists today. The total area affected by the 1811 and 1812 sequences was enormous. Intense shaking was reported from the Gulf Coast to the Great Lakes, a region larger than most European countries. Sand-blow craters from the 1812 earthquakes are still visible in aerial photographs of agricultural fields in Missouri and Arkansas today, 2 centuries later, as circular patches where the soil composition differs from the surrounding land. The scientific record of those events comes partly from journals, newspaper accounts, and the records of the United States Army Corps of Engineers, who were surveying the river at the time. Geologist Jared Brooks, living in Louisville, Kentucky, about 300 miles from the epicenter, documented hundreds of aftershocks over the winter, using a series of pendulums he built in his home. He recorded over 1,000 separate seismic events before the sequence finally quieted. The 1812 earthquakes happened on a fault few people today can name. They struck when the surrounding region held a tiny fraction of its current population, and none of its current infrastructure. The Mississippi River Bridge at Memphis did not exist. The interstate highway system did not exist. The natural gas pipelines running under the river basin did not exist. All of those things exist now. And the fault that generated 1812 is still there, still active, and approaching its next major cycle. How close that cycle is, and what the numbers say about timing, is what comes next. Geological records do not lie about frequency. Scientists can dig down into river sediment and lakebed deposits and find the physical signature of ancient earthquakes preserved in layers of sand and disturbed soil. Each major rupture leaves a mark. Sand blows in the fields. Tsunami-like wave deposits in lakebeds. Collapsed riverbank sediment buried under centuries of new material. Read those layers like tree rings, and you get a timeline. The New Madrid seismic zone has that timeline. Researchers studying sediment cores from Reelfoot Lake and nearby archaeological sites found evidence of major earthquake sequences beneath the 1812 events. One cluster dates to roughly 500 years before 1812, around 1300. Another cluster dates to roughly 500 years before that, around 800. The pattern holds back through multiple cycles, each major rupture separated by roughly 400 to 500 years. 500 years. The last major event was 213 years ago. That means the New Madrid zone is somewhere in the middle of its current cycle, not at the start, and closing toward the window when the next major sequence becomes increasingly probable. Geologists are careful not to say an earthquake is imminent, because the word imminent implies a timeline that fault science cannot provide. A 400 to 500 year cycle with natural variation could produce the next major event 50 years from now or 150 years from now. The uncertainty is real. What the uncertainty does not change is the physics. The stress accumulation driving New Madrid earthquakes is ongoing. The ancient rift beneath the zone is still a weakness in the crust. The tectonic forces pushing stress into the system have not paused. Every year that passes without a major event is another year of added strain. The question of timing is genuinely unknown. The existence of the hazard is not. The US Geological Survey estimates that a repeat of the 1812 sequence today would cause the greatest loss of life and economic damage of any natural disaster in American history. Not because the earthquakes themselves would be larger, the magnitude estimates for 1812 are roughly equivalent to what the zone can currently produce, but because of what now sits in the impact zone. Memphis sits on soft river sediment deposited over thousands of years in the Mississippi River floodplain. Soft sediment amplifies earthquake shaking dramatically. The same amplification effect described for Montana in the Tintina scenario applies here at far greater population density. Ground that would shake at a level of 6 in the open country could shake at a level of 8 or 9 in central Memphis, where the sediment layer is hundreds of feet deep. The United States Geological Survey conducted a study of the building stock in Memphis and found that a significant portion of the city's older structures, schools, apartment buildings, older commercial buildings, were built to essentially no seismic standard at all. A major New Madrid event would expose every one of those buildings simultaneously. The zone sits beneath millions of people who believe earthquake risk is someone else's problem. For most of American history, that belief seemed reasonable. The data says otherwise. And the next chapter reveals just how wide the seismic blind spot actually is. Across the entire country, pull up the United States Geological Survey's National Seismic Hazard Map, and the first reaction most people have is surprise. The expected colors show up where expected: deep red along the California coast, intense shading in the Pacific Northwest, orange tones across southern Alaska. Those are the places everyone already associates with earthquakes. Then the eye travels inward. The New Madrid zone blazes with high hazard color through Missouri, Tennessee, Arkansas, and Kentucky, right through the geographic heart of the country. South Carolina carries notable hazard from the ancient Charleston fault system, which last produced a destructive earthquake in 1886. Utah sits inside a high hazard zone driven by the Wasatch Fault running directly beneath Salt Lake City, a city of over 200,000 people built right against it. Nevada glows with hazard across most of its surface. Montana shows elevated risk. Parts of Idaho, the southern end of Illinois, northern Arkansas. 39 states, moderate to high seismic hazard. Most of their residents would be genuinely surprised to learn this. The mismatch between where people perceive earthquake risk to exist and where it actually exists is one of the most significant public safety gaps in American emergency management. It drives inadequate building codes, underfunded monitoring networks, and a near-total absence of earthquake preparedness in communities sitting on genuinely dangerous geology. Charleston, South Carolina, provides a clear example. The 1886 Charleston earthquake killed approximately 100 people and destroyed a large portion of the city. It reached an estimated magnitude 7. The cause was a fault system under the coastal plain that remains active today. In the years after 1886, building codes in Charleston were updated to reflect the new awareness. Then decades passed. Memory faded. Newcomers arrived with no knowledge of the 1886 event. The building code requirements gradually softened as the perception of risk softened. Salt Lake City presents a different kind of example. The Wasatch Fault is well understood and well monitored. Scientists have known for decades that a major rupture on the Wasatch could strike the Salt Lake Valley with intensities similar to a large California event. The city has made seismic improvements to some critical infrastructure, but a significant fraction of the building stock, particularly older brick and masonry structures in established neighborhoods, remains vulnerable to the kind of shaking the Wasatch Fault is capable of producing. The hazard map exists. The data behind it is solid. The communities shown in red and orange simply have not internalized what those colors mean in practical terms. A major earthquake preparedness organization surveyed residents in high-hazard zones across the central and eastern United States and found that fewer than 20% had taken any earthquake preparedness steps at all. Fewer than 10% knew where the nearest fault line to their home was located. The gap between what the science shows and what the public understands is enormous. And the reasons that gap persists go deeper than simple ignorance. They involve money, politics, and the hardest truth earthquake science has to deliver. That truth starts with the fault sitting closest to San Francisco, the one that scientists have been watching go further past due for decades. The last time the Hayward Fault ruptured was October 21st, 1868. A magnitude 6.8 earthquake struck on a Sunday morning, killing 30 people across the San Francisco Bay Area and destroying hundreds of buildings. At the time, the Bay Area had a fraction of its current population. The agricultural towns on the east side of San Francisco Bay, sitting directly on top of the fault, were small. The shaking was devastating for the era. That was 157 years ago. Geologists studying the Hayward Fault have built a detailed record of its past ruptures by trenching across the fault line and examining the disrupted sediment layers underground. The evidence shows that the fault ruptures on an average cycle of roughly 100 to 140 years. Past events are recorded in layers of offset sediment and folded soil that preserve each rupture like a page in a physical diary. The average interval is 100 to 140 years. The last rupture was 157 years ago. The Hayward Fault is overdue by almost every measure scientists apply to it. The United States Geological Survey currently estimates a 33% probability that the Hayward Fault will produce a magnitude 6.7 or larger earthquake before 2043. 1 in 3 odds within roughly 20 years. The fault runs directly through the most densely developed stretch of land on the east side of San Francisco Bay. It passes through Berkeley, Oakland, Hayward, Fremont, and a chain of cities totaling millions of residents. The fault trace runs beneath the University of California, Berkeley campus, beneath Memorial Stadium, beneath hospitals, schools, and major transportation arteries. In some sections, the fault is creeping slowly enough that buildings directly astride it show visible damage over time, their foundations slowly being pulled apart as the ground shifts beneath them. A major Hayward rupture today would be dramatically different from 1868. Seismological simulations called Hayward Fault rupture scenarios, run by the United States Geological Survey, estimated casualties in the range of hundreds to thousands of people, with hundreds of thousands of buildings damaged or destroyed, depending on the time of day and the precise rupture characteristics. The most damaging scenario involves a rupture during morning rush hour on a weekday, when Bay Area rapid transit trains are packed, when hundreds of thousands of people are crossing bridges and overpasses in their cars, and when school buildings that were not retrofitted to current seismic standards are full of children. Many Bay Area buildings have been retrofitted. The region has invested more in earthquake preparedness than almost any other American metro area, driven by the memory of the 1989 Loma Prieta earthquake. But the retrofits are not universal. Older soft-story apartment buildings, the wood frame structures built over ground-floor garages that collapsed repeatedly in past earthquakes, still exist in large numbers across Berkeley and Oakland. The Hayward Fault is the most dangerous fault in North America by the measure of population density directly on top of it. It is overdue. It is actively creeping in places. And the only reason it has not produced a major event in the modern era is that faults operate on their own timescale, indifferent to averages and probabilities. But something detected the hidden activity building under the Mendocino zone long before the surface gave anything away. What those signals sound like and what they tell scientists about what is coming is in the next chapter. In the years before the ocean bottom sensors revealed the hidden plates at the Mendocino Triple Junction, the data from land-based seismometers occasionally picked up something strange: low-frequency signals. Tremors that did not look like regular earthquakes. A standard earthquake produces a sharp, clear signature on a seismograph, a spike of energy, a burst of waves, a distinctive pattern that trained seismologists can identify immediately. These signals were different. They were prolonged, low-pitched, almost musical in their regularity. They lasted minutes instead of seconds. They occurred at depths consistent with the interface between subducting plates, far deeper than normal shallow earthquakes. Seismologists studying Cascadia had been observing similar signals for years and named them episodic tremor and slip events. The name describes the mechanics. At certain depths along a subduction zone, the plates do not lock completely. They slide slowly and periodically in a quiet, gradual process that produces no destructive shaking at the surface, but generates a distinctive low-frequency vibration in the rock. Think of the difference between a sharp knock on a wooden table and the low hum a table makes when something vibrates against it. Both involve motion, both produce sound waves, but they have completely different characteristics, and a sensitive enough detector can distinguish them. The low-frequency signals at the Mendocino zone were the first clue that something was happening deeper than the standard three-plate model accounted for. The signals came from the right depth for episodic tremor and slip on the Cascadia interface, but their geographic distribution did not match the expected pattern for three plates. The signals showed up in places that made no geometric sense unless something else was moving down there. When researchers deployed the ocean bottom sensors and finally had enough data to build tomographic images of the subsurface, the low-frequency signals served as a guide. They mapped where the hidden bodies were located. The Pioneer fragment was generating its own subtle tremor signal as it slid along its hidden fault surface. The descending slab fragment near the Cascadia boundary was producing signals consistent with a slab in the early stages of subduction. The tremors were the fingerprints of things that could not be directly seen. This detection method has broader implications. Low-frequency tremors have now been identified beneath other parts of North America where they were not expected, deep below parts of the Pacific Northwest, beneath sections of the San Andreas fault system where the plate interface transitions from locked to creeping, beneath portions of the Aleutian Arc in Alaska. Each detection raises the same question the Mendocino team faced. Are these tremors the signature of known, mapped processes? Or are they hints of something else moving below the surface? Something that has not yet made it into any hazard model? The honest answer is that researchers do not always know. The Earth's subsurface is enormous and imperfectly mapped. The tools for reading it are powerful but limited by sensor placement and the physics of wave propagation. Some of those tremor signals may be perfectly understood. Others may be the first faint footsteps of something waiting to be discovered. What scientists do understand is the cost of missing the signal. The Mendocino story shows exactly what that cost looks like. In science, the word revision carries a quiet kind of weight. A revised estimate sounds incremental, an update to an existing figure, a small correction to a calculation. What happened to the earthquake risk models for Northern California after the Mendocino discovery was not a small correction. It was a structural failure in the foundation of a decade's worth of planning. The models used to set building codes, design bridges, site hospitals, and plan evacuation routes for Northern California's coastal counties were built on a specific understanding of the Mendocino Triple Junction. 3 plates, a mapped set of fault surfaces, a maximum credible earthquake of roughly magnitude 8. Those inputs generated probability estimates that told planners how much shaking to design for and how often. The inputs were wrong because 2 moving bodies were missing from the picture. Adding 2 additional moving bodies to a stress model does not simply increase the risk estimate by a proportional amount. It changes the geometry of which fault surfaces are under stress, the direction of that stress, and the potential length of fault that could rupture in a single event. A longer fault rupture produces a larger earthquake. A larger earthquake generates stronger shaking at greater distances. The relationship between fault length and maximum magnitude is well established in earthquake science. The Pioneer fragment's horizontal motion extended the effective fault length of the system below what any surface survey could see. The descending slab fragment near the Cascadia boundary added stress to a section of the fault that models had treated as a transition zone. Something complex but not dangerous on its own. The updated geometry revealed that both hidden bodies were loading stress onto a fault network, larger than the one being modeled. The building codes in Eureka, California, the largest city in Humboldt County, were set based on the old model. Eureka's building stock includes a significant number of older unreinforced masonry structures, commercial buildings and apartment complexes, built in brick and mortar, without internal steel reinforcement. These structures are well understood to be among the most dangerous in an earthquake. They collapse in a characteristic way, the walls buckle outward, and the roof drops straight down. California has a mandatory retrofit program for unreinforced masonry, but many structures have received waivers or extension of deadlines. The updated risk model means those structures are facing a higher potential shaking intensity than the standard they were assessed against. An unreinforced masonry building rated against magnitude 8 ground motion may not perform adequately against the ground motion a larger event would produce. Engineers and emergency planners in Northern California's coastal counties have been notified of the revised findings. The process of updating risk assessments, revising building codes, and applying for retrofit funding is underway. But these processes move slowly. Code changes require legislative action. Retrofit programs require funding cycles. Assessment requires engineering resources. Buildings do not wait for the paperwork. The fault does not pause while the codes are revised. The gap between what the science now says is possible and what the built environment was designed to handle is real, measurable, and growing in significance with every year. The old structures stand unreinforced against a risk that turns out to be larger than advertised. This is the pattern that shows up across every fault in this story. Science advances faster than preparation. And the reason preparation lags behind is not simply ignorance. It is a specific set of structural problems that affect how earthquake safety gets funded and prioritized. That problem has a name, and it affects every fault in this video. The Alaska Earthquake Center published their Tintina findings and immediately submitted requests for expanded seismic monitoring along the fault corridor. Additional sensors, real-time data links, analysis capacity. The estimated cost for a monitoring network adequate to provide early warning capability along the Tintina's most populated sections ran to tens of millions of dollars. That request entered a federal funding cycle. It has been pending. This is not an unusual story in earthquake science. It is essentially the standard story. Research budgets that fund discovery are separate from the operational budgets that fund monitoring infrastructure. A team can spend years proving that a fault is dangerous and receive strong scientific validation for their findings. Then watch as the operational agencies responsible for monitoring that fault struggle to find the money to act on the discovery. The United States Geological Survey Earthquake Hazard Program operates on a budget that seismologists across the country have called inadequate for the scale of the risk it is supposed to address. The Shake Alert early warning system, which now covers California, Oregon, and Washington, took decades of advocacy and piecemeal funding before reaching operational status. Scientists began arguing for its construction in the 1990s. It went fully operational in those 3 states only recently, and coverage outside those 3 states remains limited. Meanwhile, the faults do not wait for budget resolutions. The problem compounds itself through the way disaster funding works in the United States. The federal government spends enormous amounts of money on disaster response after earthquakes strike, rebuilding infrastructure, housing displaced residents, operating emergency services. Studies comparing pre-disaster investment in retrofitting, monitoring, and preparedness against post-disaster recovery costs consistently find that prevention is far cheaper than response. $1 spent on seismic retrofit typically saves several dollars in post-earthquake recovery. Despite this math, funding consistently flows toward response rather than prevention. This happens because response spending is visible. It arrives with emergency declarations, news coverage, and clear political will. Prevention spending is invisible. A building that survives an earthquake because it was retrofitted generates no news coverage A monitoring system that provides 30 seconds of warning before shaking arrives, generates no dramatic story. Scientists who discover new threats walk into this system with alarming data and face a long road between the alarm and the action. The Tintina research team published their findings in peer-reviewed journals. They presented at conferences. They briefed government agencies. The scientific validity of their work has not been challenged. The monitoring infrastructure their findings call for has not been funded. The same pattern holds at Mendocino, where the updated plate count and the revised risk estimates have been published and acknowledged. But the ocean bottom sensor network that produced the discovery was a temporary deployment. The permanent expanded network that would allow scientists to track the hidden plates in real time has not been approved. Meanwhile, in the central United States, the New Madrid zone has fewer active monitoring stations per square mile of fault than California by a wide margin, despite serving a region with less earthquake culture and less individual preparedness. The science has never been better, the monitoring has never been more needed, the funding has never been more inconsistent. Every fault described in this story sits inside that gap, and the most visceral way to understand what that gap means is to picture the physical reality of what the Tintina's stored energy actually looks like when it releases. Picture a moving truck, the kind you rent when you move apartments, standard size about 20 feet from the front bumper to the back doors. Now park that truck on a flat road and draw a chalk line across the road just in front of the bumper. That chalk line is the fault. When the Tintina releases its stored 20 feet of displacement, the ground on one side of that chalk line lurches forward the full length of that truck in seconds. The ground on the other side lurches back with the same amount. The two motions happen simultaneously in opposite directions within a period of time shorter than it takes to say the word earthquake. Anything sitting on that fault line when it moves gets torn apart. A pipeline crossing the fault gets sheared at the crossing point. A road crossing the fault develops a step, a sudden vertical or horizontal offset, where the pavement on one side no longer lines up with the pavement on the other. A building foundation sitting directly on the fault rupture zone gets split, one half carried forward, one half left behind. The 20-foot slip does not happen uniformly across the entire 600-mile fault length. It concentrates at the section that ruptures, and the rupture likely involves a segment of the fault rather than the entire length in a single event. But within the rupture zone, the displacement is real, physical, and irreversible in the moments it occurs. For infrastructure, the danger is not just at the fault trace itself. The seismic waves radiating outward from the rupture produce ground accelerations, meaning the ground moves back and forth with enough force to stress structures far from the fault line. Think of it as the punch versus the shove. The fault displacement is the punch at the fault line itself, devastating in a small area. The seismic waves are the shove, pushing and pulling structures across a much wider region for the duration of the shaking. Buildings fail in shaking environments for predictable reasons. Unreinforced masonry walls lose their connection to floors and roofs and collapse outward. Soft-story wood frame buildings, the ones with parking or open commercial spaces on the ground floor, lose their ground floor support. And pancake, older concrete buildings built before modern seismic codes crack at beam column joints and shed their reinforced concrete panels. Bridges fail when their support columns crack or when the deck loses its bearing and slides off. Engineers can design against all of these failure modes. They know exactly how buildings and bridges fail in earthquakes and how to prevent it. The technology exists. The techniques exist and have been proven in modern construction. The gap is in the existing stock. Buildings already standing above the Tintina corridor, above New Madrid, above the Hayward Fault, above the Mendocino Zone. Buildings designed under old codes or no codes at all. Bridges built to standards that predate modern seismic understanding. Infrastructure running through fault zones that was put in place before the fault zones were adequately understood. The 20-foot jump is the extreme case, the worst of what the Tintina holds. But the worst case is what emergency planning is supposed to prepare for. And in most of the regions described in this story, the worst case has never been seriously planned for. What the ground itself becomes in the moments after a major rupture, especially in the specific soil conditions found along these fault corridors, is something even engineers find difficult to fully prepare for. 30 million years ago, the Pacific Ocean floor off the coast of North America was a completely different world. Where California now sits, the western edge of the continent was slowly grinding against a massive plate called the Farallon. The Farallon was a full-sized ocean plate, stretching thousands of miles from north to south, constantly generating new seafloor at its western boundary, and losing it at the eastern boundary, where it dove beneath North America. For tens of millions of years, the Farallon plate was the main geological force shaping the American West. The subduction of the Farallon plate pushed up mountain ranges. It fueled volcanic chains. It built the rock that became California, Oregon, and Washington. Every time a piece of the Farallon dove beneath the continent, it melted, and that melted rock drove magma upward, producing the volcanoes that became the Cascades and the Sierras. Then the Farallon largely ran out. The eastern portion of the plate subducted completely, disappearing into the mantle beneath North America. The western edge of the continent, freed from the compression that the subducting Farallon had been applying, began to stretch instead. The basin and range province of Nevada and Utah, that landscape of parallel mountains and flat valleys, formed because the crust relaxed and pulled apart after the Farallon stopped pushing from the west. The pieces that survived are still with us. The Juan de Fuca plate off Oregon and Washington is a surviving Farallon remnant. The Cocos plate off Mexico is another. The Gorda plate off the northern California coast is a third. The Pioneer fragment is a fourth. Each of these remnants carries the genetic signature of the original Farallon plate in its rock chemistry, and each one is still subducting beneath or interacting with North America, continuing the geological work their predecessor began tens of millions of years ago. The Pioneer fragment's behavior is distinct from the others because it did not continue to subduct in the conventional sense. Instead of diving steeply into the mantle, it became captured in the shear zone between the Pacific and North American plates and began moving horizontally. This horizontal motion is slower and shallower than subduction, which is part of why it was invisible to surface surveys. It does not produce the volcanic signatures that subducting plates produce. It does not build mountains. It moves quietly sideways, deep below the seafloor, loading stress onto the fault surfaces above it. The fact that a piece of a plate that largely vanished 30 million years ago is still generating earthquake hazard today says something important about geological timescales. Plate tectonics operates on schedules that make all of human civilization look like a single afternoon. The Farallon plate's death has been playing out for tens of millions of years, and the final chapter has not yet been written. The leftover pieces are still in motion. The stress they generate is still accumulating. The earthquakes they will eventually trigger are still building. Every fault in this story sits somewhere in that long, slow process. And the most fundamental lesson that Tintina, the Mendocino Zone, the New Madrid Fault, share is a simple and somewhat unsettling one. At first glance, a quiet fault seems reassuring. No earthquakes, no shaking, no damage. Scientists monitor it and see nothing happening, and for most people, that reads as good news. The earthquake science community sees it differently. Silence on a fault is a physical statement. It means the fault is locked. The friction holding the two sides together is stronger than the tectonic force trying to move them. The force keeps pushing, the friction keeps holding, and every year of silence is another year of stored energy added to the account. The San Andreas Fault produces earthquakes regularly. Hundreds of small earthquakes occur on parts of the fault every year. Some sections creep steadily, releasing stress gradually through constant slow motion. The regular release keeps the stored energy from building to extreme levels on those sections. Seismologists call this aseismic creep, and while it sounds alarming, A creeping fault is one that is not storing energy for a catastrophic release. The Tintina does not creep. It has not produced a significant earthquake in thousands of years. Every year of stillness adds to the balance that must eventually be paid. The same pattern holds at the southern end of Cascadia, where the locked portion of the fault has not ruptured since 1700. 325 years of quiet accumulation in a fault system capable of magnitude 9, the New Madrid Zone, silent since 1812, approaching the midpoint of its average recurrence cycle. The Hayward Fault, creeping on some sections but locked on the critical section that last ruptured in 1868. Quiet is not safety on a loaded fault. Quiet is debt. The physics behind this is straightforward. Tectonic plates do not stop moving because a fault is locked. The plates keep moving at their driving rates, centimeters per year in most cases. If the fault surface is locked, the movement gets stored as elastic deformation in the rock, the same way a rubber band stores energy when you stretch it. The rock bends, compresses, and twists around the locked section. This elastic deformation is measurable by GPS networks on the surface, and it provides a direct read of how much stored energy is in the system. When the locked section finally breaks, the elastic deformation snaps back. The rock on either side of the fault jolts to a new position. The stored energy radiates outward as seismic waves. The amount of energy released corresponds to how much elastic deformation had built up, which corresponds directly to how long the fault had been locked and how fast the plates were moving. The relationship is precise enough that scientists can calculate a fairly reliable estimate of how large the earthquake will be just from knowing the lock duration and the plate speed. That is where the 20-foot estimate for the Tintina comes from. That is why the Cascadia full rupture scenario produces magnitude 9. That is why the Hayward Fault, locked for over 150 years on its most dangerous section, is expected to produce an event larger than 1868 when it finally goes. Quieter, longer, bigger. Every fault in this story has been quiet for a long time. The science on that is clear. What governments and communities do with that information is the part that remains uncertain, and that is where the story ultimately lands. The Shake Alert system covers California, Oregon, and Washington. It works. During a 2019 magnitude 6.4 earthquake near Ridgecrest, California, alerts reached smartphones in the Los Angeles area several seconds before the shaking arrived. Automated systems at certain facilities received the warning and took protective actions. The system demonstrated in real conditions exactly what the engineers who built it promised it could do. Expanding that system to the rest of the country is a matter of politics and funding, not technology. A nationwide early warning network would require thousands of additional seismometers deployed across the central and eastern United States, along the Tintina Corridor in Alaska, across the New Madrid Zone in the Heartland, along the Wasatch Front in Utah, and through every other region identified as carrying significant seismic hazard. Each sensor requires installation, power, a communication link back to a processing center, and ongoing maintenance. The sensors themselves are not expensive. The deployment, maintenance, and data processing infrastructure across a continent-scale network represents a significant investment. Seismologists who have advocated for the expansion put the cost in the range of a few $100 million for the sensor infrastructure, with ongoing annual operating costs in the tens of millions. Compared to the estimated losses from a single major earthquake in an unprepared region, which run into hundreds of billions of dollars and include economic disruption that continues for years, the investment looks extremely rational. The benefits go beyond individual alert times. A denser sensor network produces better data on fault behavior. Better data improves hazard models. Improved hazard models lead to better building codes, better infrastructure siting decisions, and better emergency planning. The return on a monitoring investment compounds over time. Several cities and states have started their own preparedness investments without waiting for federal action. Salt Lake City has conducted detailed fault rupture scenarios and updated its emergency response plans specifically for a Wasatch Fault event. Memphis has a dedicated earthquake preparedness initiative. Seattle has made significant investments in retrofitting critical infrastructure for the Cascadia scenario. But individual city initiatives cannot substitute for a coherent national approach. Seismic waves do not stop at city limits. A major New Madrid event would affect multiple states simultaneously, overwhelming any single state's emergency capacity. Coordinated response across state lines requires pre-event planning that only works if every participating state has been operating with the same hazard data. The scientific community is unified on what is needed: dense monitoring, updated hazard models, revised building codes applied to vulnerable existing structures, early warning systems in all high-hazard regions, public education so that people in moderate hazard states understand their risk and know what to do in the first few seconds of shaking. The window to act is always the same in earthquake preparedness. Before the earthquake, every action is possible. After the earthquake, the only action available is response. The science providing the warning exists. The technology to act on it exists. What exists less reliably is the political will to fund prevention when no earthquake has recently struck, to make the urgency feel immediate. But the hardest truth earthquake science carries is not about funding or politics. It is about the fundamental nature of fault behavior itself. And that truth makes everything else in this story feel even more urgent. A geophysicist once described fault science with a metaphor that stuck with the field. Studying a fault is like studying a bridge by watching how it sways in the wind. You can measure the sway, you can calculate the stress in the steel, you can know exactly how strong the bridge is rated, but you cannot know exactly when a particular crack in a particular girder will finally propagate through the metal and bring the span down. The physics of fault failure is well understood at the large scale. Stress accumulates. At some point, the friction holding the fault together fails. The fault slips, an earthquake happens, the cycle resets and begins again. Every element of that process is grounded in solid physics. The part that resists prediction is the failure threshold. Rock is not a uniform material. Every fault contains sections with different mineral compositions, different roughness profiles, different amounts of fluid pressure in the pore spaces between rock grains. Fluid pressure matters enormously. Water or other fluids in rock reduce the effective friction, making it easier for a fault to slip. A change in fluid pressure from seasonal groundwater fluctuations, from a distant earthquake disturbing the local stress field, from deep volcanic activity far below, can nudge a fault closer to failure without any visible surface signal. This is why the Tintina's 20-foot slip deficit does not come with a date attached. The physical reality of 20 feet of stored displacement is solid. The calculation behind it is reliable. The fault will release that energy. The timing is genuinely unknown. It could be 50 years from now. It could be 5 years from now. It could be this year. The stored energy does not expire on a schedule. The same uncertainty applies to every fault in this story. The Hayward Fault is overdue by historical standards, but the historical record covers only a handful of past events. The average interval could have more variation than the record shows. The Cascadia Fault could hold its lock for another 100 years. The New Madrid Zone could produce its next major sequence decades ahead of the average cycle, or decades behind it. Scientists are careful about how they communicate this uncertainty because the temptation in public communication is to remove it, to say something like the big one is coming in the next 20 years and generate immediate attention and funding, but that framing would be dishonest. The science does not support a precise timeline. What the science does support is clear. Every fault described in this video is under significant and measurable stress. Every one of them has a history of major ruptures. Every one of them will rupture again. The accumulated evidence from multiple independent research programs, from satellite surveys and drone mapping, and ocean bottom sensors and sediment cores, all points in the same direction. These faults are loaded. They are closer to failure than the public understands, and the regions above them are less prepared than the hazard warrants. That is the honest message earthquake science is currently delivering. Not a prophecy with a date, but a statement of physical reality backed by data from every tool the field has available. The faults are ready. The preparation is not. And the gap between those two things is what the final chapter of this story is about. The morning after a major earthquake on a forgotten fault is not a movie disaster scene. It is slower, more confusing, and in many ways harder than any screen version captures. Cell networks go down within minutes of a major event, not because the towers collapse, though some do, but because millions of people try to make calls simultaneously and the system buckles under the load. For several hours after a major earthquake, most people in the affected region cannot reach anyone. They do not know if family members at work or school are safe. They do not know if the damage to their neighborhood is isolated or widespread. They are making decisions with almost no information. Water systems fail. Pipelines cross fault lines and sediment-filled ground. Ground-shaking ruptures distribution pipes underground. Reservoirs lose their supply lines. In a major event affecting a city like Memphis or Fairbanks, water service disruption can last days to weeks, not hours. Without water, hospitals cannot operate normally. Fire suppression becomes nearly impossible at the moment fire risk is highest, because gas line ruptures and downed electrical lines start fires across the affected zone simultaneously. Bridges fail. The road network that emergency vehicles depend on becomes impassable in key locations. The first responders who survive the earthquake in their stations cannot reach the populations who need them most. People trapped in collapsed buildings wait. Every hour of waiting reduces survival odds in the rubble. This is not catastrophizing. This is the operational record of every major urban earthquake in modern history, from Northridge to Kobe to Christchurch to the 2023 events in Turkey. The pattern is consistent and well documented. The most powerful thing an individual can do is eliminate or reduce their personal dependence on the systems that fail first. Water storage is the highest priority. Emergency management agencies recommend at least 1 gallon per person per day for a minimum of 3 days, ideally 2 weeks. A family of 4 storing 2 weeks of water is genuinely more resilient than a family with nothing set aside. Stored water does not need to be expensive. Large food-grade containers from hardware stores work perfectly. Securing heavy furniture and appliances to walls eliminates a major injury risk during shaking. Most earthquake injuries come from falling objects, not building collapse. Bookshelves, refrigerators, and water heaters that tip and fall cause a significant fraction of earthquake casualties. Furniture straps cost a few dollars at any hardware store. Knowing your building's construction type matters. Soft-story buildings with open ground floors, older unreinforced brick structures, and pre-1980s concrete buildings carry higher collapse risk than modern wood frame construction or steel buildings built to current seismic codes. Knowing what you live in tells you how much additional concern is warranted and whether retrofit options exist. The drop, cover and hold on protocol, endorsed by earthquake scientists worldwide, means dropping to your hands and knees, taking cover under a sturdy table or against an interior wall away from windows, and holding on until the shaking stops. This single action reduces injury risk significantly. It costs nothing to practice. The faults described in this story are real. The stress stored in them is real. The populations sitting above them are real. Preparation does not require certainty about timing. It requires accepting that the ground beneath you has a history, and that history will eventually repeat. The science has done its job. It found the faults nobody was watching. It measured the stress nobody was counting. It issued the warning. The next move belongs to us.